these were the methods of preparation of alkyl halides from alcohols. Okay. Next, we will prepare alkyl halide by using some other substrate from hydrocarbons, from alkenes, from alkenes. Okay. So one by one we will discuss today. Preparation of alkyl halide from hydrocarbon. First is from, let us know, from alkene. Okay. After alkene, we will know the method from alkane. This is from alkene. Let us know fast. As you have done, these are unsaturated hydrocarbons. Okay, where carbon-carbon double bonds are present. These alkenes undergo electrophilic addition reaction. Just try to remember this. Electrophilic addition reaction is one of the very important reactions exhibited by alkene molecules. So, in order to prepare alkyl halide, we need to treat alkenes with some suitable reagents such that the electrophilic addition reaction could be taken place, and as a result of which we can obtain alkyl halide. Okay, the reagent is the addition of halogen acid HX. Once again, we need to use the same reagent. This reagent was already used with alcohols. Today, we will use the same reagent with alkene. Addition of halogen acid HX. Okay. Let me write the general equation. This is the representation of alkene. When this alkene that be treated with HX molecule, HCl, HBr, HI, then as a result of the reaction, as I told you, this is electrophilic addition reaction. This can be written here as, this is symbolized like this, AD, that is for addition, and E is electrophilic. As a result of this electrophilic addition reaction, you will get one addition product where the carbon-carbon double bond that will be converted into single bond. Because in HX molecule, these two parts, one is electrophilic part and second one is the nucleophilic part. This is your electrophilic part, H plus partial positive charge, partial negative charge. Okay, this part will be added to one carbon. The another part will be added to another double bonded carbon. Across this double bond, the addition will occur. Okay. So, for example, let us consider this hydrogen that is getting added to this carbon, then this halogen that will be added to this carbon, then we will get our product as, this is your required alkyl halide. Okay. For example, let me take some simple alkene fast. It is one alkene, ethene. When it be treated with HBr, then as a result of the chemical reaction, what we get? Here these two carbon which are doubly bonded. Okay, these two carbon, they are under same chemical environment. Okay, this is called as symmetrical alkene. And in symmetrical alkene, you need not to think about, you need not to be confused whether this carbon will get hydrogen, that carbon will get halogen. Okay, this kind of confusion is not observed when your alkene is symmetrical. So, this hydrogen that can be attached to any of these two carbons. Let us consider here, I am attaching this hydrogen, then CH2 that will be converted into CH3. Double bond will be converted into single bond, and this bromine that will be added to this carbon, then we will get the product CH3CH2Br, ethyl bromide. From ethene I got ethyl bromide. Okay. Similarly, Another alkene molecule, let us consider CH3, CH double bond, CH single bond, CH3. Due to in when this be treated with HCl, tell me in the same way what will be our product. This is also another symmetrical alkene. Okay, this hydrogen that can be added to this carbon or this carbon, you will get the same product. Okay, so our product would be CH3 CH2. If hydrogen that we consider to be added to this carbon, then CH2, this double bond will be converted into single bond, and this Cl that is to be added to another doubly bonded carbon CH. This CH group that was attached with CH3 and this carbon that contains the Cl. For your convenience, just I am writing here the H which has been added separately. Okay, these two carbons, they were having double bonds in the substrate molecule, but in your product, this HCl molecule, this is your addendum, the species which is getting added, that is called addendum. One part of this addendum that has been added to this carbon, another part that has been added to another doubly bonded carbon. This carbon contains the hydrogen and this carbon contains the chlorine. So this is your required product. This is your desired product. Okay. Let us consider when the alkene is not symmetrical. Not symmetrical. If your alkene is not symmetrical, let us consider CH3 CH double bond CH2 propene. Propene molecule. This is not symmetrical alkene because across this double bond, the carbon, they are not under same chemical environment. Okay, this carbon contains only 2 hydrogen, but this doubly bonded carbon that contains 1 hydrogen and 1 methyl group. So the atoms or groups which are attached to the doubly bonded carbons are not same. That's why this is not symmetrical alkene. And when this symmetrical alkene that we treated with one HX molecule, there is chances of formation of 2 alkyl halide molecules as products. Okay, one product that will be obtained when this hydrogen that will be added to this carbon, then the chlorine that will move to this carbon, as a result of which we will get one product CH3 CH single bond CH2. The double bond was here. If hydrogen be added to this carbon and chlorine be added to this carbon, then we will get this product. Okay. Also, the second case, the second chance that can be considered here, when hydrogen that will be added to this carbon, this terminal carbon, and chlorine that will be added to the middle carbon, then you will get your product CH3 CH Cl single bond CH2 that will become CH3. Okay. So these are 2 possible products. When your alkene is unsymmetrical, if alkene that is symmetrical, then you need not to be confused because both the carbons, both the doubly bonded carbons, they are same. Okay. Whereas when the alkene is unsymmetrical, you need to think whether this product will be formed or this product will be formed in measure amount. Okay, and in order to find the measure product, you need to know about the mechanism of the reaction. If we are not using the mechanism also, we can apply a rule in order to find the measure product, that is called as Markovnikov's rule. Markovnikov's rule. Okay, Markovnikov's rule. According to that rule, negative part of the addendum that goes to that doubly bonded carbon which contains less number of hydrogen. Once again, I repeat. According to Markovnikov's rule, the negative part of the addendum, which is the addendum, the species which is getting added. Here HX is the addendum, HBr is the addendum, HCl is the addendum, HCl is the addendum. This is addendum. So according to Markovnikov's rule, the negative part of the addendum, if this would be the addendum, then which one is the negative part? Due to polarization, partial negative charge will be developed over this chlorine. This is your negative part. This is your negative part, this is your positive part. So according to Markovnikov's rule, the negative part of the addendum that goes to that doubly bonded carbon which contains less number of hydrogen, this is your alkene. These are the two carbons which are doubly bonded. This middle carbon that contains only one hydrogen, but this terminal doubly bonded carbon that contains two hydrogen. So out of these two carbon, this carbon contains less number of hydrogen. So according to rule, just try to apply the rule. Negative part of the addendum that will move to this carbon which contains less number of hydrogen. This chlorine is to be added to this carbon. Then when chlorine that we added to this middle carbon, then which product out of these two products, which product is obtained? This is your product which is obtained in measure amount. Okay, this would be your measure product. We need to know the basic mechanism here. What happens actually? This is your substrate molecule CH3CH double bond CH2. This is your alkene molecule. Okay. When HX be added, HX, as HX I have taken HCl. Okay. This carbon-carbon double bond, it contains pi electron cloud, and due to presence of pi electron cloud, it acts as the source of electron. Due to presence of this pi electron cloud, it acts as the source of electron, and it generally interacts the electrophilic spaces, the electron deficient spaces fast. So in HCl, which one is the electrophilic part? Partial positive charge that is getting developed over hydrogen. This pi electron cloud that will interact with this hydrogen part. This bond is polarized. Partial negative charge that has been developed over chlorine, that is simply due to the difference in the electronegativity. So this electron cloud that will interact with this positive part, as a result of which this bond will be broken and this pair of electrons will be completely separated to the chlorine. Then what you will get as a result of this interaction, you will get one carbocation intermediate. Carbocation. As this is your unsymmetrical alkene. Unsymmetrical alkene. Two chances are there. Two possibilities are there. That means two types of carbocations may be formed. When this H plus ion that will be attached to the middle carbon fission. This is your CH3 group. This is CH. Double bond was there. Next, I need to put single bond because this electron cloud now it is going to be used. By the help of this pi electron cloud, when a bond will be formed between this hydrogen and any of this carbon atom, then we will get the carbocation. If this carbon will bind the hydrogen, if the middle carbon that will bind this hydrogen, then obviously a positive charge will be developed over the terminal carbon. And similarly, if this terminal carbon will bind this hydrogen, this is your terminal carbon CH2 that will bind the hydrogen. I have shown here. Then the middle carbon that will have positive charge. So these are two carbocation species. These are two possible carbocation species. When the hydrogen that we attach to the middle carbon, you will get this carbocation, and when hydrogen that will be added to this terminal carbon, the middle carbon will get the positive charge. This is the second carbocation. If we observe these two carbocation species, so the first carbocation is a primary carbocation, positive charge that is over the primary carbon, right? And the second carbocation species, that is a secondary carbocation, positive charge that is over the secondary carbon. One is primary carbocation, this is primary carbocation, and this is a secondary carbocation. Whenever the possibility of formation of two different carbocations be there, then obviously that carbocation will be formed in measure amount which is more stable. Higher the stability, easier is the formation of any species. So out of these two carbocation species, this carbocation stable, secondary carbocation is more stable as compared to primary. That's why this will be formed easily or male. So in measure amount you will get this carbocation species. Okay, this is your first step. I'm talking about the mechanism of the above reaction. Mechanism. In the first step, formation of carbocation occurs, and in the next step, the carbocation. Let me take the measure carbocation here. CH3CH, CS3 plus. This is the secondary carbocation. This carbocation will be formed in measure amount. Okay, that's why I have taken here. This H plus that has been already added to the alkene. Cl minus is there. Now the Cl minus ion that will be added. Okay, this is your nucleophile. Cl minus that will be directly added to this carbon atom. Then you will get CS3, CH, CS3. Here the chlorine will be added. This is your final alkyl chloride product. Okay, and when this carbocation will be considered, the Cl minus, when it will be added to this carbon, you will get another alkyl chloride. This alkyl chloride. I have shown this alkyl chloride which is obtained in measure amount by applying Markovnikov's rule. Also, we have shown this was the measure product. And here we explain why actually this product is formed in measure amount. Okay, try to understand. Two main steps, two important steps I have shown here in the mechanism of this reaction. In the first step, the formation of carbocation occurs. This is electrophilic addition. This is your electrophile, and addition has been occurred. This has been added. As a result of this electrophilic addition, in the first step we are getting carbocation. Okay, we need to consider the stable carbocation. Then this is your stable carbocation. This stable carbocation, in the next step, the negative species, after the addition of the positive part, the remaining negative part that will be added to your carbocation such that you will find a final product. And out of these two steps, the first step, which involves the formation of carbocation, that is the slowest step. If we compare the relative rate of these two steps, the speed of these two steps, experimentally it has been found that the first step, it is slower one. Okay, this step, that is slower one. Okay, the step involving the formation of carbocation, that is slowest step here. So if we apply kinetics, chemical kinetics, then what happens? In slowest step is the rate determining step. That determines the rate of overall reaction. That means this step will determine the overall reaction. In this step, as two species are involved, one is your alkene and second one is the HX molecule, then the rate of this reaction will be influenced by two concentration species. One is your alkene and second one is your HX. That's why this is a second-order reaction. Second order. Here the rate law that can be written here as rate is equal to K into concentration of alkene. Concentration of alkene and concentration of HX. This is HX. This is alkene. This is your slowest step. This step will determine the rate. So rate equation that can be written here like this. The rate is equal to K into concentration of alkene into concentration of HX. Okay. If we compare the relative reactivity of various halogen acids, HCl, HBr, HI, towards a given alkene, then what would be the order? Equation. In the first step, this bond is getting broken. If I take HI, then HI bond will be broken. If HBr be taken, then hydrogen bromine bond will be broken. And if HCl be taken, then hydrogen chlorine bond be broken. The bond which can be broken easily, this step will occur faster. Then if we compare the bond strength in HI, HBr and HCl, then what happens? the bond in Hi is weakest. In case of HCl, that is strongest. Okay, that's why the bond in Hi molecule that will be broken easily. The hydrogen ion, the H plus ion, that can be added easily. That means this passage that is going to lose its H plus ion. These are the acids. So stronger the acid, easier is the addition of H plus ion. And also we have done among HCl, HBr, Hi is the strongest acid. Easily it can form H plus ion. Easily it can release H plus ion. The H plus ion of Hi, it can be easily added to the alkene molecule. So the order of reactivity among halogen acid is Hi is greater than HBr is greater than HCl is greater than HF. Okay, so this is the relative order of reactivity of various halogen acids towards the given alkene. Similarly, if we compare the relative reactivity of various alkene molecules towards a given halogen acid, if we compare the relative reactivity of various alkenes, now we will fix the halogen acid. We will consider one halogen acid. Towards the same halogen acid, we will compare the relative reactivity of various alkenes. Let me consider three alkene molecules here. Three alkene molecules. One is ethene. Second one is propene. And third one is isobutylene. Okay. So these three alkenes, among these three alkenes, we need to compare the relative reactivity towards the same halogen acid. What can you predict? How can you compare? Alicia, this is the mechanism of electrophilic addition reactions of alkenes with halogen acid. Okay. All these alkene molecules, they will undergo the same reaction via the same steps. We need to think about the fast step. This is the slowest one. This will determine the rate of overall reaction, or this will determine the relative reactivity of this alkene molecule. Listen, student. The halogen that is same for these three alkene molecules. Okay. If we assume this alkene molecule as our substrate, then in the fast step we will get a carbocation. Which type of carbocation? CS3. This will be your carbocation. If this H plus that we added to any of these two carbon, then you will get this carbocation. When this alkene be considered, already I have shown here the same alkene. When this alkene that is getting added in the fast step, we are getting these two carbocation intermediates. Okay, two possibilities are there. However, we will think about the more stable carbocation. So this is your carbocation which is obtained when this alkene be used as substrate. Okay, and whenever we will think about this alkene, when this alkene will participate in this reaction, then there also, as it is one of the unsymmetrical alkene, here also possibilities of formation of two carbocation are there. And again, once we need to think about the more stable carbocation. These are the doubly bonded carbons. When hydrogen be added to this carbon, positive charge will appear over this carbon, that is primary carbocation. And when hydrogen be added to this carbon, positive charge will appear here, it is tertiary carbon, so you will get the tertiary carbocation. So after primary and tertiary carbocation is more stable. So I need to manifest the tertiary carbocation, the formation of tertiary carbocation here. Now try to compare what we are doing. We need to compare the relative reactivity of these three alkene molecules. Okay, and we can compare by comparing the relative stability of these carbocations intermediate which are to be formed. When this alkene molecule be taken for the reaction, you will get this carbocation in the slow state. When this be used, this carbocation will be formed, and when this alkene be used, this carbocation will be formed. What have we done? Out of these three carbocations, this is tertiary carbocation, this is secondary carbocation, this is primary carbocation. So this is the most stable carbocation. That means this species it can furnish most stable carbocation. Among these three alkene molecules, these alkene that can furnish most stable carbocation. That's why the reaction of this alkene be faster, because it can furnish most stable carbocation. The first step, if we compare this step for these three alkenes, here the first step will occur easily. Then this next step. So which is more reactive? This is most reactive alkene. The reactivity of this alkene is highest where it is lowest. So in this way we can find the order. This is the order of reactivity of various alkene molecules. Okay. So this is about the relative reactivity of halogen acids towards a given alkene and the order of reactivity of various alkenes towards a given halogen acid. You have to remember what have I told today. If I need to prepare alkyl halide from alkene, then first of all we need to think whether the given alkene is symmetrical or unsymmetrical. This is symmetrical alkene. When HX be added to it, then you will get one alkyl halide. You needed to be confused. This is symmetrical alkene. Okay? But when unsymmetrical alkene be given, this is one of the unsymmetrical alkene. Let us add HBr molecule. This is unsymmetrical, so here we need to apply Markovnikov's rule. Okay, already we have discussed it. Whenever unsymmetrical alkene be there, you need to think about Markovnikov's rule in order to get your measure product. So we will apply Markovnikov's rule. This is the carbon, doubly bonded carbon, which contains less number of hydrogen. The negative part of the addendum that will go to this carbon which contains less number of hydrogen. So negative part is bromine. Bromine that will move to this carbon. Then what would be your product? CS3. This CH2 will become CS3 because this hydrogen that is going to be added to this carbon CS3 and bromine will appear here. Okay, this is your final product. Here Markovnikov rule is to be applied because the alkene is unsymmetrical, and when the alkene is symmetrical, you needed to think about Markovnikov's rule. Okay, you can add your negative part or the positive part to any of the doubly-bonded carbon. Okay, next, Kharas effect or peroxide effect. Okay, whenever any unsymmetrical alkene that be added to HBr, particularly HBr, we needed to think about HCl or HM. So whenever any unsymmetrical alkene that be added with HBr in the presence of peroxide, some organic peroxide, benzoyl peroxide is generally taken. In the presence of peroxide, if this addition reaction be carried out, then your measured product is obtained in anti-Markovnikov manner. That is the reverse of Markovnikov's rule. Here, peroxide is not present. In the absence of peroxide, we are carrying out this reaction. Then here we need to apply the Markovnikov's rule. But the same reaction, when it be carried out in the presence of some peroxide, then this would be your minor product, because the reaction that will occur through anti-Markovnikov manner. That means the opposite product here, the negative part of the addendum, now it will move to that doubly bonded carbon which contains more number of hydrogen. That is anti-Markovnikov rule. Okay, opposite to the Markovnikov rule. CS3, CS3. Next, single bond CH2. Here the bromine will be added, CS2, Br, and hydrogen that will be added to this carbon. This is opposite product. This would be your measured product. Always remember, in the presence of peroxide, and this is particularly for HBr, not HCl, not HI. Whenever HCl or HI be given in the presence of peroxide, if the reaction be carried out, then there is no change no deviation in the Markovnikov rule. Okay, you have to apply the same rule. But when HBr be added to unsymmetrical alkene in the presence of some peroxide, then the reaction occurs through anti-Markovnikov manner, anti-Markovnikov rule. Okay, this would be the measure product in the presence of peroxide. This is called peroxide effect or Keras effect. Okay. Another point which is to be noted here, I have shown the mechanistic pathway. In general reaction, electrophilic addition reaction, I have shown the mechanistic pathway, the various steps. How many steps we have shown? 2. In the first step, a carbocation intermediate was getting formed, and in the second step, after the formation of carbocation, the negative part will be added. You will get the final product. Okay. As these reactions, they involve the formation of carbocation intermediate. If that carbocation which has been formed initially, that can be changed into relatively more stable carbocation through 1,2-hydride shift or 1,2-alkyl shift, which is called as the rearrangement we have learned in our previous classes. Okay, those reactions which involve the formation of carbocation intermediate, and if those carbocation, they can be converted into more stable carbocation through 1,2-hydride shift or 1,2-alkyl shift, then the rearrangement will occur fast. And after the rearrangement, the remaining step will occur and final product will be formed. Okay. For example,